In this section, we're going to be talking about free energy. Free energy is represented with a capital G. We also refer to that as Gibbs Free Energy. The equation that we use most often is this one here, and that's delta G is equal to delta H minus T delta S. So delta G is Gibbs free energy. That's how much free energy you have. When delta G is negative, that means the reaction proceeds on its own. It's a thermodynamically favored reaction. If it's positive, then that's how much energy you're going to have to put into the reaction for the reaction to proceed. Delta H is our enthalpy, and that's generally in kilojoules per mole. T is temperature, it needs to be in Kelvin. And delta S is entropy, that's generally in joules per Kelvin times mole. So make sure that you convert delta S from joules to kilojoules. You can also convert your delta H to joules, but most often we convert our delta S to kilojoules to get our delta G in kilojoules. So a reaction is thermodynamically favored or spontaneous, depending on what textbook you're looking at. Sometimes it says spontaneous, sometimes it says thermodynamically favored. But the AP test does like thermodynamically favored now. If delta G is negative, that's when it's thermodynamically favored, if it's carried out under constant pressure and temperature. Since we can't measure delta G directly, we can use other measured quantities to calculate our delta G. The more negative the value of delta G, the further a reaction will go to the right to reach equilibrium. We can also relate delta G to equilibrium, which we'll see in the next part. So this problem wants us to calculate the delta G, and they gave us the delta H and delta S. So we're going to be plugging it into this equation. We're looking for delta G. Delta H was negative 393.5, and that's kilojoules. Minus our temperature is 298, and it's already in Kelvin. Times our delta S. And our delta S we need to convert to kilojoules, so dividing by 1,000. I get 0.00305. So my delta G is negative 394.4 or negative 394. For this problem, they want us to figure out which reaction will be the most spontaneous or most thermodynamically favorable. That's going to equal the most negative delta G. For all the reactions, it says delta S is 0. Well, if our delta S is equal to 0, then our T delta S has to equal 0. So really, all of that is 0. So delta G is equal to delta H in this case. So the more negative our delta H, the more negative our delta G. So that must be D, since it's the most negative delta H. This problem, they want you to calculate the delta H, the delta S, and then the delta G. We don't know the delta H, but we know the delta H is a formation. Same thing, delta S, we have delta S as a formation, so we can use the delta H's and delta S as a formation by doing products minus reactants. Once we have those two, then we can plug it into our delta G equals delta H minus T delta S. Go ahead and pause the video and get your delta H value and your delta S value. Restart when you have those two. So delta H, you should have got a negative 198, and delta S, negative 187. And that's kilojoules and joules, respectively. Go ahead and pause the video and calculate delta G. Restart when you're done. So for your delta G, you should have converted your delta S to kilojoules, so that was negative 0.187. Plugging that in, you get negative 142. So this reaction is thermodynamically favorable since we have a negative delta G. In the upper left corner, this reaction is a non-spontaneous process, or not thermodynamically favorable. Delta G is positive. It takes energy to get that boulder up the hill. So it's not that the reaction can't occur, energy just has to be put into the reaction for it to occur. A spontaneous process, delta G is negative. This would be thermodynamically favorable. The boulder goes down the hill all on its own. No energy is needed for the boulder to go down the hill. When delta G is 0, then it's at equilibrium. And the boulder just never chases you up the hill. So that's a non-existent process. Some problems will ask you, when is this reaction thermodynamically favorable? At high temperatures, at low temperatures, always, never. So that's when this chart comes in handy. You're going to have delta H on one side of the chart and delta S on the other. It doesn't matter which one. And then one's positive, one's negative. One positive, one negative. Then you have to ask yourself, more entropy, less entropy. Which one does the universe go towards? More disorder. This one's favored. And then if the reaction is going to go on its own without having to do anything to the reaction, exothermic is going to be favored. So exothermic and more disorder drive spontaneity or drive thermodynamically favored processes. Therefore, if both things, delta S and delta H, are both for spontaneity, then it's going to be favorable at all temperatures. If neither entropy or enthalpy are favored, then it will never be spontaneous, no matter what the temperature is. If both temperatures are positive or both temperatures are negative, then that's when it's going to be temperature dependent. If they're both positive, delta G will be negative at high temperatures. And if they're both negative, delta G will be negative at low temperatures. The reason being is delta G is equal to delta H minus T delta S. If delta H and delta S are both positive, right now my delta H is against thermodynamically favorability. So I want my H to matter very little. I want my S, which is for spontaneity, to matter more. In order for it to matter more, I need a high temperature. The higher the temp, the more that S will matter because it's being multiplied, making that product larger. So that way it can overcome the positive delta H. If my delta H and delta S are both negative, then I want my delta H to matter more, so I want my temperature to be low, so that way my product of temperature and delta S is a very small number in comparison to my delta H. So what exactly is high and low, and how do we figure that out? So in this process, or this problem, it says, at what temperature is the following process spontaneous? Notice my delta H is positive and my delta S is positive. So I know that at high temperatures, it's going to be spontaneous or thermodynamically favorable, but what exactly will be a high temp? So to solve this problem, we're going to use our delta G equals delta H minus T delta S equation. But we're going to set delta G to 0. So 0 is equal to 31 minus T and then times 0.093 kilojoules. Because again, we have to convert our joules to kilojoules. Solving this out, temperature is equal to 333 Kelvin. That's the normal boiling point of liquid bromine. This is a liquid, this is a gas, so at equilibrium, it would be boiling, and this is our equilibrium temperature. But to figure out at which temperature will this occur, we want high temps, so any temp that is greater than 333 Kelvin will be a thermodynamically favorable process. So 334, 335, 340, 700, anything greater than 333, it'll be thermodynamically favorable. So on this problem, go ahead and figure out at what temperatures will this reaction be thermodynamically favorable. So you should have used the same equation. Just like before, both of these are positive. So we get 82.99 or 83 Kelvin. Since we want a high temperature, any temperature greater than 83 will be thermodynamically favorable. If this problem was a negative 24.2, then we would have got a negative 83 Kelvin, which makes sense because negative delta H and positive delta S should be all temperatures. Well, the lowest temperature Kelvin can get is 0, so negative 83 means that all temperatures must be spontaneous because all temperatures will be greater than negative 83 Kelvin. So if you get a negative Kelvin, it means that all temperatures are spontaneous. We can solve for delta G by a couple of different methods. We can use number 1, which we've been using. We can also take advantage of the fact that delta G is a state function and solve it like Hess's law, just like we've done for delta H and delta S. And we can also use delta G as a formation by doing our products minus our reactants. So the sum of the moles of our products minus the sum of the moles of our reactants. This one, they give you 2 equations, and we're trying to find the delta G of this third equation, so we should be using it like Hess's law. So go ahead and pause the video and figure out the delta G of this reaction, restarting when you're done. The first reaction you should have reversed because we need 2 COs. Reversing it gives me a positive delta G, and that reaction no longer exists. I need 2 CO2s as a product. Well, I have CO2 here, so I should double this reaction. So I've got my CO2, my waters cancel out, my CH4s cancel out. I have oxygen on both sides, so the smaller one goes away. This turns into a 1. So I've got all of my pieces, so I'm just going to add those up. Adding that up, I get negative 514 kilojoules. Go ahead and pause the video and solve this one on your own. Restart when you're done. So we wanted C diamond as a reactant. We have C diamond as a reactant. We want C graphite as a product, so we need to reverse that second reaction. So then canceling out, we have oxygen on opposite sides, we have CO2 on opposite sides, we have everything we want. So we just add those up and we get negative 3 kilojoules. So this reaction is thermodynamically favorable. So diamonds spontaneously or thermodynamically turn into graphite, but you don't see people's wedding rings turning into graphite overnight, even though it's thermodynamically favorable, because kinetically it's too slow. So although reactions are thermodynamically favorable, we also need kinetic data to know will the reaction happen in a feasible amount of time. On this problem, they give you the delta G's of formation. So go ahead and pause the video and figure out your delta G of formation based on that balanced equation. So solving that out, you should get negative 1378 kilojoules per mole, which again is very spontaneous or very thermodynamically favorable. That's a large negative number. All right, in our last problem, we have a chemical engineer who's trying to make ethanol. They can react ethylene with water, and so figure out, is this reaction thermodynamically favorable? Restart when you have your answer. So you should get negative 6 kilojoules per mole, which is thermodynamically favorable. So this reaction could occur as long as the kinetic data also is going to occur in a reasonable amount of time.